In the summer of 1964, a physicist in Edinburgh mailed a paper to the most important particle physics laboratory on Earth. The paper described where mass comes from, why anything in the universe weighs anything at all, why your body holds its shape instead of flying apart at the speed of light. They rejected it. The word that came back, relayed to him secondhand, was that his work had no obvious relevance to physics. That man was Peter Higgs. 48 years later, a $10 billion machine, 17 miles of tunnel, 10,000 scientists, and roughly 1,000 trillion proton collisions confirmed that he had been right, and he sat in the auditorium at 83 years old and wiped his eyes. That should have been the whole story. It is not, and the reason is buried in the number the machine handed back. 125 gigaelectron volts. Run that number through the equations and it tells you something about the ground beneath reality that almost nobody has been willing to say out loud. Tonight we go through all of it, the rejection letter, the one sentence he added out of wounded pride that named the particle and won him a Nobel Prize, the referee who turned out to be a future Nobel laureate and said nothing for 20 years, the collider abandoned under Texas farmland with its tunnels already dug, the colleague who died 1 year before the confirmation and 2 years before the prize, and the thing the measurement quietly revealed about the vacuum you are sitting in right now. Get comfortable and subscribe or join if you have not already. There is also a Patreon where these explorations run wider and deeper across physics, space, mathematics, and collapse. Stay to the end, because by the time we get there, you will understand why the solidity of everything you have ever touched is not a law. It is a setting, and it is not resting where you think it is. Let's ease into it. Reach out and touch something. The desk, the phone in your hand, your own arm, whatever is closest to you right now. That thing you just touched has weight. It resists you. Push on it and it pushes back. And every teacher you ever had, every textbook you were ever handed, gave you the same explanation for why. Mass is how much stuff a thing is made of. More stuff, more mass. It is the very first thing anyone learns about matter, and it is one of the most quietly wrong ideas in the whole of physics. Not a little wrong. Wrong at the foundation. Wrong in a way that took the entire 20th century to notice, and then took a single sentence, added almost in irritation, to a rejected paper in the summer of 1964 to begin to fix. Here is what is actually true. The weight of the thing you just touched does not come from the thing. It comes from something the thing is sitting inside. There is a field. It fills every cubic centimetre of space in the room you are in the space between your hand and this screen, in the vacuum between the stars. It does not switch off. It has never switched off since the universe was a fraction of a second old. And it has a value, a strength, that physicists have measured to be roughly 246. 246 gigaelectron volts, if you want the unit, which is a unit of energy standing in for mass, and we will come back to what that number means. For now, understand only this. That field is the reason you are not weightless. It is the reason the electrons in your body have any mass at all. It is the reason atoms hold their shape instead of flying apart at the speed of light. Switch that field off, set its value to 0, and you do not lose weight. You cease to have a body. Every particle in you would fly apart at light speed and there would be no you to notice. That field has a name now. You have probably heard the name attached to a particle, and you have heard it wrong, and we are going to spend the next 2 hours taking that wrongness apart piece by piece. But the field itself, the thing doing the work, the thing filling the vacuum right now as you breathe, was described for the first time in a paper that a scientific journal looked at and rejected. The editors, working out of the most important particle physics laboratory on Earth, decided the paper had, and this is close to the phrase that came back, no obvious relevance to physics. The paper described the origin of mass, the reason anything in the universe weighs anything at all, and the gatekeepers of physics read it and saw nothing. I want you to sit with how strange that is before we go anywhere else, because it is going to become the spine of this whole story, the single most consequential idea in modern particle physics, the idea that eventually cost $10 billion in 30 years and the labour of more than 10,000 people to confirm, the idea that won a Nobel Prize and rewrote the standard textbook account of why the universe has substance, was very nearly never printed. A man in Edinburgh wrote it down over a weekend, sent it off, and got told it was not interesting. His name was Peter Higgs, and the story of what he wrote, what was done to it, how long he waited, and what the answer turned out to be when it finally came back from the machine, is stranger and darker than the tidy version you have been handed. Because here is the part almost nobody tells you. When the machine finally found the particle he predicted, when the champagne was poured and the old man in the auditorium wiped away tears, the number that came back was not just a mass. It was a warning. The value of that field, the precise strength of the thing that gives you weight, sits balanced on an edge, and no physicist alive can tell you why it is balanced there, or how long it will stay. We will get to the edge. I need you to hold that word. Edge. It is going to come back 3 times before this is over, and each time it is going to mean something worse. The question I want to keep open, the one that this entire story is really about, is not where the Higgs boson came from. That is the safe question, the one the documentaries ask. The real question is this: where does the weight of the universe actually come from? And why is the thing that supplies it poised on a knife edge that the people who understand it best cannot explain and mostly refuse to discuss in public? Let me start with the man, because you cannot understand the physics until you understand how close we came to never hearing about it. Peter Higgs was born on the 29th of May, 1929, in the Elswick district of Newcastle upon Tyne, in the northeast of England. His father was a sound engineer for the British Broadcasting Corporation, and the family moved often, which meant that a good part of Higgs's early education happened at home, in relative isolation, a boy reading his way through subjects on his own. He was frequently ill as a child, asthmatic, kept out of school for long stretches. If you are looking for the origin of the reclusive, self-contained man he became, it is probably somewhere in those quiet years spent teaching himself. He ended up at Cotham Grammar School in Bristol, and there is a detail from those years that matters more than it should. On the honours board at that school was the name of a former pupil. Paul Dirac. One of the strangest and most precise minds in the history of physics, the man who predicted antimatter by taking an equation seriously enough to believe what it told him even when it told him something absurd. The young Higgs became fascinated by Dirac, by the idea that you could sit with mathematics and have it hand you a piece of the universe that nobody had ever seen. That is a specific kind of faith, and Higgs caught it early. The belief that if the equations say something is there, then it is there, and your job is to go find it. Remember that. It is going to matter enormously in about 30 years of story time when Higgs writes down a sentence saying, "A particle must exist," and then spends nearly half a century waiting for the rest of the world to go and find it. He studied at King's College London, took a first-class honours degree in physics, finished a doctorate in 1954, and then he did the thing that quietly defined his whole career. He moved to Edinburgh, to the University of Edinburgh, and he stayed. He was not a man who chased conferences and fame and the circuit of big physics. He was a man who wanted peace and quiet and a problem to chew on. By his own admission, decades later, he was not what a modern university would call productive. He published very few papers. He would go years without putting anything out. And he was fine with that, because he was not trying to build a resume. He was trying to understand something. Years later, after the whole world knew his name, he said something about this that should stop anyone who works in a modern institution cold. He said that today, in the current academic system, no university would employ him. He would not be considered productive enough. He said he had become an embarrassment to his department when the time came for research assessment, when they asked every academic for a list of recent publications, and he would send back a statement saying, quite simply, none. He said it was hard to imagine ever having enough peace and quiet in the present climate to do what he did in 1964. Think about what that means for a moment. The man who solved one of the deepest problems in physics is telling you that the system as it exists now would have chewed him up and spat him out before he ever got the chance. That the conditions that let him think, the slowness, the isolation, the freedom to be unproductive for years, are exactly the conditions the modern research machine has optimized out of existence. He is not the last casualty of that pattern. He might be the last person who escaped it. But we are getting ahead of the story. Go back to 1964. Higgs is 35 years old, a junior lecturer at Edinburgh, not famous, not senior, working on a problem that most of the leading physicists of the day considered either solved or unimportant. And over one weekend, that summer, something clicked. He always resisted the mythology that grew up around this moment. There is a popular version where Higgs walks in the Cairngorm Mountains, has a flash of insight on a hillside, comes down transformed. He denied it was anything so cinematic. What he described was quieter and, honestly, more believable. Over a weekend, he gradually realized that he knew two things that had to be brought together. Two separate pieces of physics that nobody had connected, and that when you connected them, a door opened. He said there was no single eureka moment. It was a slow dawning across a weekend, and then he had to go back into his office on the Monday and check that he had not made a mistake. He had not made a mistake. He would later call it the only really original idea he ever had. He told his biographer, the physicist Frank Close, that the portion of his life for which he is known amounts to about 3 weeks in the summer of 1964. 3 weeks. Out of 94 years of living. That is the whole of it. Everything the world remembers him for happened in 3 weeks, and then he spent the remaining half-century waiting to find out whether he had been right. Here is the problem he was chewing on, and I am going to give it to you the way it actually sat in front of him, because the shape of the problem is the whole point. Physics in the early 1960s had a theory it loved and a theory that did not work, and they were the same theory. The framework was gauge theory, the deep mathematical idea that the forces of nature come from symmetries, from things you can change about your description of the universe without changing the physics. It is one of the most beautiful ideas anyone has ever had. It explained electromagnetism perfectly, and when physicists tried to use the same beautiful machinery to describe the other forces, the forces inside the atomic nucleus, it produced a catastrophe. The mathematics insisted that the particles carrying those forces had to be massless. They had to weigh nothing, exactly like the particle that carries light, the photon, which is genuinely massless. But the particles that carry the weak nuclear force are not massless. They are heavy. Extraordinarily heavy, as particles go. And the theory that was supposed to explain them predicted, with total confidence, that they could not be what they visibly were. The equations demanded zero. Reality delivered something enormous. And for years the best physicists in the world were stuck, because every attempt to give those particles mass by hand smashed the beautiful symmetry that made the theory work in the first place. You could have the symmetry, or you could have the mass. You could not, it seemed, have both. There was a theorem in the way. It was called the Goldstone theorem, named for the physicist Geoffrey Goldstone, and it said, in effect, that if you break one of these symmetries to give your particles mass, you are punished. The universe hands you back a useless massless particle, a ghost, that nobody had ever seen and that should have been everywhere. This theorem was regarded as close to a law. It looked like a locked door. It looked like proof that the whole approach was a dead end. And what Higgs realized over that weekend was that the locked door had a hinge nobody had looked at. That under the right conditions. When you took the symmetry breaking and combined it properly with a gauge field, the useless ghost particle did not appear as a ghost at all. Instead, it got absorbed. It became part of the force-carrying particle itself, and in doing so, it gave that particle exactly the mass the theory had said it could not have. The ghost was not a punishment. The ghost was the mechanism. The very thing everyone thought was fatal to the theory turned out to be the solution, if you had the nerve to look at it the right way. That is the Higgs mechanism, stated as plainly as it can honestly be stated. The symmetry breaks. Empty space fills with a field, and that field gives the force carriers their weight, while quietly eating the ghost that the old theorem had promised. He wrote it up. 2 short papers back to back in the summer of 1964, and this is where the story turns from a story about physics into a story about how physics actually works as a human institution, which is to say, badly, and with almost no awareness of what it is holding in its hands. The first paper went to a European journal called Physics Letters, which was edited out of CERN, the European Organisation for Nuclear Research, the great particle physics laboratory near Geneva. That first paper was accepted and published. Fine, it laid the groundwork. But it was the second paper, the one that actually contained the model, the one that spelled out the consequences, that mattered. And Higgs sent that one to the very same journal, Physics Letters, at CERN. It came back rejected. The editor told him the paper was not suitable for the journal as it stood, and suggested he expand it into a fuller account and send it somewhere else, to an Italian journal called Il Nuovo Cemento. That was the formal response, and Higgs was, in his own word, indignant. He felt that whoever had refereed the paper had simply not seen the point of it. He was not wrong to feel that way. Because a little while later, a colleague came back from spending a month visiting CERN and told him what the theorists there actually thought. They did not think the paper had any relevance to particle physics. That is the origin of the phrase that has followed this story ever since. No obvious relevance to physics. It was not written in an official rejection letter in those exact words. It was relayed to Higgs, secondhand, as the general opinion of the theory group at the most important physics laboratory in the world. They looked at the mechanism that gives the universe mass, and they shrugged. I want to be precise about what happened here, because it would be easy and cheap to turn this into a story about idiots missing genius. And that is not quite it. The people at CERN were not fools. They were some of the sharpest minds of the century. What happened is more unsettling than stupidity. It is that the field had collectively decided which questions were interesting and which were not. And the origin of mass, framed the way Higgs framed it, simply fell outside the boundary of what respectable theorists were supposed to care about that year. It was not rejected because it was wrong. Read that carefully. It was rejected because it did not look important. And in physics, as in every human institution, looking unimportant is far more dangerous than being wrong. A wrong idea gets attacked, argued with, engaged. An idea that looks unimportant gets a polite note suggesting you try a different journal. The paper had been turned away at CERN, And here is where the rejection, the thing that should have been the end, becomes the reason you know his name at all. Higgs did not send the paper to the Italian journal the editor suggested. Instead, annoyed, determined, he decided to revise it and send it across the Atlantic to the American journal Physical Review Letters. And because he had been stung by the rejection, because he felt the point of his work had been missed, he sat down to extend the paper, to spell out its consequences more forcefully, to make it impossible to ignore what the theory actually implied. In his own words later, he thought he had better give some indication of the consequences. And in doing that, in adding material to a rejected paper out of something close to wounded pride, he wrote one sentence. One sentence that he almost did not write, in a paragraph that only exists because his first attempt had been thrown back at him. The sentence noted that an essential feature of this kind of theory is the prediction of what he called incomplete multiplets of scalar and vector bosons. Strip away the jargon, and here is what that sentence says. This theory does not just fix the mass problem, it predicts a new particle, a specific, findable, real particle, a heavy one, that should exist and could one day be detected. That scalar boson is the Higgs boson. That sentence, added in irritation to a paper that had just been rejected for having no obvious relevance to physics, is the entire reason the particle carries his name. Higgs said this himself plainly more than once. He got credited with the particle because he was the one who pointed out that it was there, and he only pointed it out because the first version of his paper had been rejected and sent back to him, and he was annoyed enough to extend it. And there is a detail here that turns the whole thing into something close to poetry, if you find institutional irony poetic, which by the end of this you might. The referee assigned to Higgs's revised paper at Physical Review Letters, the person who read it and asked him to revise, was a physicist named Yoichiro Nambu. Nambu was no ordinary referee. He would go on to win his own Nobel Prize decades later, in 2008, for related work on how symmetries break in nature. And it was Nambu who asked Higgs to add a comment on how his paper related to the work of Brout and Inglet in Brussels, whose paper had just appeared. Until that request, Higgs had no idea the Brussels work existed. The referee was the one who connected the isolated man in Edinburgh to the two men in Brussels, who had beaten him to publication by weeks. And Higgs would not learn who his referee had been until 20 years later, in 1984, when he met Nambu at a conference, and Nambu revealed that he had, in fact, refereed both papers. One man at Physical Review Letters had quietly stood at the centre of the whole thing, holding the papers of rival groups in his hands, and said nothing for 2 decades. The people who understand these things are often standing much closer to the centre of them than the public ever learns. Let me make sure the weight of this lands properly. The most sought-after particle in the history of science, the target of the single most expensive experiment ever built by human beings, the thing that thousands of physicists across more than 100 countries would spend their careers hunting, exists in the historical record as a particle first, because a man in Edinburgh got a rejection slip and decided to prove a point. If physics letters at CERN had simply accepted the second paper as written, that sentence might never have been added. The particle might have been called something else, credited to someone else, or drifted for years as an unremarked mathematical footnote. The rejection is not a footnote to the discovery. The rejection is why the discovery has his face on it. But he was not alone. This is the part the tidy version flattens. And it matters, because the story of who found this thing is a story of how credit in science gets assigned, and it is not always assigned to the people who deserve it most. In that same year, 1964, the same idea was found independently by 2 other groups of physicists, working separately in different countries, unaware in real time of what the others were doing. In Brussels, at the Free University, 2 physicists named Robert Brute and François Inglet had worked out essentially the same mechanism and had actually submitted their paper before Higgs submitted his. Their paper was received in June of 1964 and published at the end of August. Higgs, isolated in Edinburgh, did not even know their work existed, because the Brussels group did not send their preliminary papers around to places like Edinburgh. Two teams had cracked the same door open on the same continent in the same season, and neither knew about the other. And there was a third group. At Imperial College London, 3 physicists, Gerald Guralnick, Carl Hagen, and Tom Kibble, arrived at the same mechanism from yet another angle. Their paper was received in October of that year, published in November. 3 independent teams, 6 physicists, 1 idea, all within a few months of each other in the year 1964. When an idea is that ready to be found, when it falls out of the sky into 3 separate laboratories at once, it tells you the idea was sitting there in the structure of physics, waiting, and the only question was, who would reach up and take it? There is a name buried even further back that honesty demands we mention. An American physicist named Philip Anderson had, a couple of years earlier, described something very close to the core of this mechanism in the context of superconductors, of how certain materials behave at very low temperatures. Anderson had it, in a sense, first. Higgs said as much himself, generously, that Anderson really got it right but that nobody understood him, because he had phrased it in the language of condensed matter physics rather than particle physics, and the particle physicists were not listening to the people who study cold metals. The idea was there, it was just speaking the wrong dialect to be heard. Why do we say the Higgs boson and not the Brout boson or the Anderson boson or, God help us, the Anderson-Brout-Inglet-Higgs, Guralnick-Hagen-Kibble boson, which some careful physicists do actually try to say? The answer comes back to that one sentence. Of all 6 men working in all 3 groups, Higgs was the one who explicitly wrote down that the theory predicts a specific new massive particle you could go and detect. The others had the mechanism. Higgs pointed at the boson and said, "That is real, go find it." In a field built on the faith that if the equations say something is there, then it is there. The man who pointed at the thing and named it as findable is the man whose name sticks. He learned that faith from a name on a school honours board in Bristol. Dirac predicted antimatter by believing his equation. Higgs predicted the boson by believing his. The line runs straight from one to the other. Now, before we go deeper into what this field actually is, I have to correct something, because you have almost certainly absorbed a piece of nonsense about this particle, and it is worth clearing out of the way early. You have probably heard the Higgs boson called the God particle. It is a terrible name, and every serious physicist I have ever read on the subject hates it, and its origin is far more petty than divine. The phrase comes from the title of a 1993 popular science book by the Nobel laureate Leon Lederman, and Lederman did not want to call it the God particle at all. According to Lederman himself, he wanted to call it the goddamn particle, because of how maddeningly hard it was proving to find, how much money and effort it was swallowing with nothing to show. His publisher would not allow the profanity, and goddamn became God. A marketing decision got mistaken for a theological statement, and a generation of people came away with the idea that physicists think this particle is somehow divine. They do not. Higgs, who was an atheist, particularly disliked the name and worried it would offend religious people, and pointed out wearily that it had started as a joke. The most famous nickname in modern physics is a censored curse word. That is the actual origin. Hold on to that, because this whole story is full of moments where the real version is smaller, stranger, and more human than the legend, and full of other moments where the real version is very much larger and darker than anyone let on. We are about to hit one of the larger ones. Everything so far has been about a man and a paper and a sentence. Now I need to tell you what the sentence was actually about, because the field it describes is far stranger than the phrase giving mass to particles makes it sound, and the strangeness is not a detail. The strangeness is the whole story, and it is where the dread starts. Start with the thing you were probably told, so we can take it apart. The popular version goes like this. The Higgs boson gives everything its mass. Particles move through the Higgs field like people wading through water or walking through a crowd, and the resistance they feel is their mass. It is a nice image. It is on 1,000 websites, and it is misleading in at least 3 separate ways, each of which opens onto something more unsettling than the tidy picture admits. The first correction is the one that matters most, and almost nobody knows it. The Higgs field does not give everything its mass. It does not even give most things their mass. Take an ordinary object, your own body, a rock, a glass of water. The overwhelming majority of the mass in ordinary matter, something like 98 or 99% of it, has nothing directly to do with the Higgs field at all. Here is why. Your body is made of atoms. Atoms are mostly the mass of their nuclei, and nuclei are made of protons and neutrons, and a proton is made of 3 tiny quarks held together by the strong nuclear force. If you add up the masses of those 3 quarks, the masses they get from the Higgs field, they account for only about 1% of the mass of the proton. 1%. The other 99% is pure energy. It is the raw binding energy of the strong force, the ferocious field holding the quarks together, converted into mass by the most famous equation in physics. Energy equals mass times the speed of light squared. Almost all of your weight, almost all of the weight of every ordinary thing you have ever lifted, is not substance. It is the energy of a war being fought inside every proton in your body. A war that has been raging since the universe was seconds old and will not stop until the protons themselves decay, if they ever do. You are not heavy because you are made of heavy things. You are heavy because there is a storm inside you that never ends. When someone tells you the Higgs boson gives everything its mass, they are wrong by a factor of about 100. The Higgs is responsible for maybe 1% of the mass of the visible universe. But here is why that 1% is not a footnote. Why it is in fact the difference between a universe and nothing. The particles that do get their mass from the Higgs field, the electrons, the quarks themselves, the carriers of the weak force, would without it be massless. And a massless electron cannot be bound into an atom. It travels at the speed of light and cannot be caught. Turn off the Higgs field, and that 1% vanishes, and every atom in existence unbinds instantly. There would be no chemistry, no molecules, no structure, no you. The Higgs does not supply most of your weight. It supplies the small piece without which the rest could never assemble into anything. It is the mortar, not the bricks. And a wall with no mortar was never a wall to begin with. It is a heap of dust that never got to stand. The second correction is the difference between the field and the boson, and it trips up almost everyone, including a lot of science journalists who should know better. The Higgs boson does not give anything mass. The boson is not the thing doing the work. The field is. The field is the invisible presence filling all of space, switched on everywhere. Always. The boson is something else entirely. The boson is a ripple in that field, a disturbance. If the field is the surface of a vast still ocean covering the entire universe, the boson is a single wave you make by slapping the water hard enough, and to slap the Higgs field hard enough to make even one wave, one boson. You need to concentrate an enormous amount of energy into a tiny point of space, which is exactly why it took the largest machine ever built to do it. Finding the boson did not prove the field gives mass. The field had been doing its quiet work for 13.8 billion years regardless. Finding the boson proved the field is really there by disturbing it hard enough to make it ring. We went looking for the wave to prove the existence of the ocean. The third correction is the deepest, and it is the one that should genuinely change how you feel about the word mass. We say the Higgs field gives particles mass, as if mass were a substance being handed out. It is not. Mass for these particles is a relationship. It is the strength of a particle's interaction with the field it is sitting inside. An electron has the mass it has because of how strongly it couples to the Higgs field. A more strongly coupled particle is heavier. A weakly coupled one is lighter. A particle that does not couple at all, like the photon, has no mass and moves at light speed forever. The mass of the electron, then, is not a fact about the electron. It is a fact about a relationship between the electron and something else, something external, something filling the space around it. Take the electron out of the field, which you cannot actually do because the field is everywhere, but imagine it, and its mass is not reduced. Its mass is undefined. Meaningless. Mass is not a property a particle carries around like a colour. Mass is something that happens to a particle because of where it is and what it is swimming in. I want to slow down here because I think the strangeness of this gets lost in the numbers. We are taught to think of weight as the most solid, obvious, undeniable thing about the physical world. You put something on a scale and it reads a number, and that number is what the thing is. But that number is not what the thing is. That number is a description of a conversation, an ongoing conversation between the thing and a field it cannot escape, a field it did not choose to be in, a field that was here before it and will be here after it. Your weight is not yours. It is on loan, moment to moment, from something that fills the emptiness you thought was empty. Which brings us to the emptiness, because this is where the physics stops being merely surprising and starts being something I still do not fully know how to think about. We call the vacuum empty. Space between the stars, empty. The gap between your hand and this screen, empty. It is not empty. It cannot be empty, because the Higgs field is there, and it has a value, and that value is not zero. Remember the number from the very start of this, 246. That is the value the Higgs field sits at throughout all of space. Physicists call it the vacuum expectation value, which is a technical phrase meaning the amount of this field you would find if you looked at a patch of pure vacuum and measured. And what you would find is not nothing. You would find 246 gigaelectron volts of field, uniform, everywhere, in the deepest, emptiest void you can imagine. This is the thing that should reorganize your intuition. There is no such thing as empty space. What we call empty is a region flooded with a field at a value of 246, and it is precisely because that value is not zero that anything has mass, that atoms hold together, that you exist to hear this. Emptiness is not the absence of everything. Emptiness is the presence of the Higgs field at rest. The void is not a void, it is a substance pretending to be nothing. And now the question that no textbook asked me when I was young, the question that runs underneath this entire story. Why is the value 246? Why that number? Why not zero, in which case nothing exists, or some enormous number? In which case the universe looks completely different and equally hostile to life. The field settled on a value early in the universe's history, as everything cooled from the fire of the first moments, and it found a place to rest. It settled into a valley, a low point, a stable configuration where it has stayed ever since. And here is the sentence I need you to carry forward, because we are going to come back to it, and it is going to be the whole ending. The field found a valley to rest in. The disturbing part, the part we will return to, is that it may not be the deepest valley available. It may be resting in a dip on the side of a mountain, comfortable, stable seeming, for now. And if there is a deeper valley somewhere below it, then the ground you are standing on is not the floor, it is a ledge. There is that word again. Ledge, hold it. We are one layer down now, and there are more. To understand how the field settled into its valley, you have to understand the moment it chose. And I am using that word chose deliberately, because it is closer to what happened than the passive language usually allows, and because the way the universe made this choice is one of the eeriest things in all of physics. In the first instance after the beginning, when everything was unimaginably hot, the Higgs field did not have the value it has now. It sat at 0. Everything was massless, everything moved at light speed, and the universe was in a state of perfect symmetry, beautiful and balanced and sterile. Nothing could form, nothing could hold, and physicists picture the situation the field was in using a shape, and the shape matters, so build it in your mind. Imagine the bottom of a wine bottle, the kind with a dome pushed up in the centre. Or picture a sombrero, a hat with a raised bump in the middle and a circular brim falling away around it. At the very beginning, the field was balanced on the top of that central bump, perfectly symmetric, perfectly unstable, a pencil balanced on its point. A pencil balanced on its point does not stay balanced. It falls, and it has to fall in some direction, and there is no reason for it to prefer any one direction over another, so it simply falls, and in falling it breaks the symmetry that held while it was upright. That is what the Higgs field did as the universe cooled. It rolled off the central peak and down into the circular valley of the brim, and it came to rest at a value of 246. And in doing so it broke the perfect symmetry of the early universe and gave the world mass. The universe did not decide in advance where the field would land. It fell, the way a pencil falls, in a direction that was not written anywhere beforehand. The masses of every particle, the structure of matter, the possibility of atoms and chemistry and stars and you, all of it descends from an arbitrary tumble the universe took in its first moments, a symmetry breaking with no author, choosing a direction for no reason, and then locking that choice in for the entire subsequent history of everything. That is not a metaphor I am imposing on the physics. That is the physics. The field broke its own symmetry. It selected a configuration out of infinitely many equivalent ones, and every solid thing you have ever known is a consequence of which way the pencil happened to fall in a universe less than a trillionth of a second old, and the consequences of that tumble reach much further than whether your atoms hold together. They reach all the way to the sun in the sky, and to the fact that it has been shining gently for billions of years rather than detonating in an instant. Follow this, because it is the chain that connects that first arbitrary fall to your being alive to hear about it. Remember what problem Higgs was originally solving. The carriers of the weak nuclear force, the particles called the W and the Z bosons, were mysteriously heavy when the theory said they should be massless. The Higgs mechanism is what made them heavy, and a force whose carrier particles are heavy behaves in a way that changes everything downstream of it. It becomes short-ranged and feeble. A force carried by a massless particle, like electromagnetism carried by the massless photon, reaches across the universe and is strong. A force carried by a heavy particle can barely reach across the width of an atomic nucleus, and its effects at everyday energies are almost vanishingly weak. That is exactly why the weak force is called weak. It is not weak by some independent decree. It is weak because the Higgs field made its carriers heavy, and heavy carriers make a feeble, short-ranged force. The weakness of the weak force is a direct fingerprint of the Higgs field's value. Now go to the center of the Sun. The Sun shines by fusing hydrogen into helium, and the very first step in that process, the one that gets everything started, requires two protons to come together and one of them to transform into a neutron. That transformation is a weak force event. It can only happen through the weak nuclear force. The feeble one. The one the Higgs field made feeble. And because the weak force is so weak, that first step is agonizingly, almost unbelievably slow. A given proton in the core of the Sun, jostling against other protons at millions of degrees, will wait, on average, billions of years before it successfully undergoes that transformation and begins to fuse. Billions of years. In the heart of a star, at temperatures that beggar imagination, the crucial first step of fusion is so improbable that any individual proton waits longer than the current age of the Earth to take it. And that slowness is the whole reason you are alive. Think about what it would mean if the weak force were not weak. If the W and Z bosons were light. If the Higgs field had never made them heavy. That first fusion step would not be slow. It would be fast. The Sun would not be a steady furnace metering out its fuel across 10 billion years. It would burn through its hydrogen in a geological eye blink, or explode, or never settle into a stable star at all. The reason the Sun is a patient, long-lived, gently warming star. The reason it has been shining at a roughly constant brightness for the 4.5 billion years it took for life on Earth to crawl out of the oceans and eventually build a machine to find the Higgs boson, is that the weak force is weak. And the weak force is weak because the Higgs field made its carriers heavy, and the Higgs field made its carriers heavy because of the direction it tumbled. In the first trillionth of a second of the universe, sit with the length of that chain. An arbitrary, ortholess symmetry breaking at the dawn of time set the value of a field. That value made the weak force carriers heavy. That heaviness made the weak force feeble. That feebleness made the first step of stellar fusion slow. That slowness made the Sun a steady furnace instead of a bomb. And that steadiness gave life the billions of years of gentle, reliable sunlight it needed to exist at all. The sunlight falling on your skin is meted out at a rate set, ultimately, by the value the Higgs field fell into before the universe was a billionth of a second old. You are not just held together by this field. You are warmed by it, slowly, deliberately, across billions of years, and you were given the time to come into existence by the same accidental tumble that gave your electrons their mass. The field that decides you have a body is the same field that decided the Sun would be patient enough to wait for you. Now hold all of this. The field, the value, the valley, the broken symmetry, the ledge, because a man in Edinburgh had written down that a particle must exist as the signature of all of it, and the world was about to spend nearly half a century and more money than anyone had ever spent on a single scientific question, trying to find out whether he was right. And Higgs, the whole time, was not sure he would live to see it. Consider what it actually takes to find a Higgs boson, because the gap between the modesty of the prediction and the enormity of the search is one of the strangest ratios in the history of human effort. The prediction was a sentence. A single sentence, added to a rejected paper, taking up a couple of lines on a page, written by one man at a desk in Scotland with a pen. To test that sentence, human beings built the Large Hadron Collider. The Large Hadron Collider being the enormous particle accelerator run by CERN beneath the border of France and Switzerland near Geneva. It is a ring 27 kilometers around, about 17 miles, buried as deep as 100 meters below farmland and suburbs. A circular tunnel so long it crosses an international border underground. It was built over roughly a decade, from the late 1990s into 2008 by a collaboration of more than 10,000 scientists and engineers from hundreds of universities across more than 100 countries. The cost ran into the billions. Depending on how you count the machine and the experiments and the years of operation, the figure people usually reach for is around $10 billion. $10 billion, 10,000 people, 17 miles of tunnel to check whether a sentence written in 1964 was true. Inside that ring, protons are accelerated to very nearly the speed of light. So close to it that the difference is a rounding error and sent around the loop more than 11,000 times every single second. Then they are steered into head-on collisions, hundreds of millions of collisions per second, and at 2 points around the ring sit two of the largest and most complex scientific instruments ever constructed, two separate detectors called Atlas and CMS. Two detectors, built and run by two separate teams of thousands of physicists each, deliberately kept independent, so that neither could accidentally convince the other of something that was not real. Each detector watches the debris of the collisions, reconstructs what particles were born and died in each tiny fireball, and sifts through an ocean of data looking for the rarest of signatures. And it is rare almost beyond comprehension. A Higgs boson is not produced in most collisions. It is produced in roughly 1 in billions, and when it is produced, it does not stick around to be photographed. It exists for a span of time so short there is barely language for it, a tiny fraction of a nanosecond, and then it decays, falls apart into other particles. And it is only those decay products, the shrapnel, that the detectors ever actually see. Nobody has ever seen a Higgs boson. What they saw was the specific pattern of debris that a Higgs boson leaves behind when it dies, appearing slightly more often than it should if there were no Higgs boson, a small bump in a graph, a faint excess in the noise. To find it, the collaboration sifted through something on the order of 1,000 trillion proton collisions. 1,000 trillion. To find the fingerprint of a particle that Peter Higgs had predicted in a sentence he almost did not write, 48 years earlier. 48 years. Think about what that number contains as a span of a human life. When Higgs wrote that sentence, he was 35, a junior lecturer nobody had heard of. By the time the machine was ready to render its verdict, he was 82, an old man, long retired, who had spent decades being famous for a prediction that had never been confirmed, watching the search grind on, aware that the answer might not arrive before he died. Physicists knew where to look. Roughly, they had narrowed the possible mass of the particle down over the years, closing in, ruling out range after range. But narrowing is not finding. And a man in his 80s does not have unlimited years to wait for a machine to finish deciding whether the one original idea of his life was real or a beautiful mistake. But the Large Hadron Collider was not the first machine sent to hunt this particle, and the story of the ones that came before it, the ones that missed, is its own quiet tragedy, and it stretched the wait out year by agonizing year while Higgs got older. The first serious attempt was American, and it was going to be bigger than anything Europe ever built. In the 1980s, the United States began construction on a machine called the superconducting supercollider, a particle accelerator whose ring would have been more than 50 miles around, dwarfing the collider that eventually found the Higgs. It was being built beneath the plains of Texas, near a town called Waxahachie, and it was explicitly designed to find the Higgs boson and open the era beyond the standard model. Miles of tunnel were bored, nearly $2 billion was spent, and in 1993, the United States Congress, weary of ballooning costs and unconvinced of the payoff, voted to cancel it. The project was killed with the tunnels already dug. The holes were eventually sealed or sold off. Tens of kilometers of abandoned tunnel under Texas farmland, the most expensive hole ever dug for a question that got no answer. Leon Lederman, the physicist whose book gave the particle its unfortunate nickname, had written that book in part as a public plea to save the funding for exactly this machine. The goddamn particle was, among other things, an argument for a collider that Congress then cancelled anyway. The book outlived the machine it was written to defend. Therefore, the search crossed back to Europe, to CERN, to a machine called the Large Electron Positron Collider, which ran through the 1990s inside the very same 27-kilometre tunnel that would later house the Large Hadron Collider. In the final months of its life, in the year 2000, as it was being prepared for shutdown to make way for its successor, some of its detectors saw something, a faint excess, a hint of a possible Higgs boson at a mass around 115 gigaelectronvolts, right at the very limit of what the machine could reach. It was not strong enough to claim a discovery, nowhere near the 5 sigma standard, but it was tantalizing, and the physicists who saw it begged for more time. Pleaded to extend the machine's run by a few months to chase the hint. CERN's management faced an agonizing choice: extend the old machine and delay the new one, or shut down on schedule and build the future. They shut it down. The hint was never confirmed, and never fully ruled out by that machine. It simply went dark, mid-question, because the tunnel was needed for something bigger. Imagine being one of the physicists who saw that excess, and then watched the machine that saw it get switched off, before it could tell you whether you had glimpsed the thing everyone had spent their lives chasing. And there was one more, back across the Atlantic. At the Fermi National Accelerator Laboratory near Chicago, a collider called the Tevatron spent the 2000s hunting the Higgs, narrowing the possible mass range from the sides, closing in, ruling out territory, doing everything but landing the final blow. It never quite had the energy or the data to make the discovery, and in 2011, the Tevatron was shut down, out of funding, 1 year before the Higgs was finally confirmed just across the ocean. It came so close, it missed by a year and a machine. Count them. An American supercollider cancelled with its tunnels already dug. A European machine switched off in the middle of a tantalizing hint. An American machine shut down 1 year short of the answer. The particle Peter Higgs predicted in a rejected paper did not just take 48 years to find. It outlasted a cancelled collider, a sealed tunnel under Texas, and 2 machines that were switched off before they could finish the job. The weight had a body count, and the bodies were some of the most expensive scientific instruments ever built. All of it, every tunnel and every shutdown and every year, riding on whether one sentence added in irritation in 1964 was true. And then came the summer of 2012. On the 4th of July, 2012, CERN called a seminar. The room was packed. People had queued through the night to get a seat. Students in sleeping bags outside the auditorium, because the rumour had gone around that this was going to be the day. And Peter Higgs, then 83 years old, was in the room. He had been invited. He sat and he waited to hear, from a machine that 10,000 people had built, whether the sentence he wrote at 35 was true. The 2 teams presented separately, and that separation is important because it is the whole reason anyone believed the result. The Atlas team went, led by the physicist Fabiola Gianotti, and reported a new particle in their data at a mass around 126 gigaelectronvolts, with a statistical significance that crossed the threshold physicists demand before they will use the word discovery. Then the CMS team went, led by the physicist Joe Incandela, and reported the same thing, independently, from their own separate detector and their own separate analysis. A new particle at around 125 gigaelectronvolts. 2 machines, 2 teams, thousands of people who had been kept deliberately walled off from each other had both found the same bump in the same place. Incandela describing it, said plainly that this was a new particle, that it had to be a boson, and that it was the heaviest boson ever found. The threshold they crossed is called 5 sigma, and it is worth understanding what that phrase actually promises, because the whole discipline hangs on it. 5 sigma is a measure of how unlikely it is that what you are seeing is a random fluctuation, a fluke in the noise rather than a real signal. 5 sigma means the odds of the result being a random accident are about 1 in 3.5 million. Physicists do not say discovery until they have crossed that line, because the history of the field is littered with 3 sigma bumps that melted away when more data came in. This one did not melt. It got sharper. Both teams had it. The particle was real. And in the auditorium, Peter Higgs took off his glasses and wiped his eyes. He was seen crying, and afterward people asked him why, and his answer is one of the most human things any scientist has ever said about a moment of triumph. He said that during the talks he was still keeping his distance from it all, still holding it at arm's length the way he had held it for decades, because for 48 years the smart thing had been not to get your hopes up. But when the seminar ended, he said, it was like being at a football match when your own team wins, and the feeling rose up and knocked him over like a wave. 48 years of held breath let out all at once, in a lecture hall, in front of the world. He flew back to London afterward, and in the most gloriously understated gesture imaginable, celebrated with a single can of beer, a London pride on the plane. An old man, alone with a can of beer at 30,000 feet, having just watched the universe confirm the one idea of his life. He had genuinely not been sure this would happen while he was alive. He had said as much, more than once, that the confirmation might not come in his lifetime. It came with 11 years to spare. He died in April of 2024 at 94 in Edinburgh, in the city where he had done the work 60 years before. He got to know. Not everyone in this story did, and we are about to get to the ones who did not, because the confirmation that brought Higgs to tears also carried a quieter cruelty, and beneath that cruelty sat something worse than any of it, hiding inside the very number the machine had just delivered. The year after the discovery, in October of 2013, the Nobel Prize in Physics was announced. It went to Peter Higgs and to François Englert, the physicist from the Brussels group, for the theoretical prediction of the mechanism that the machine had now confirmed. 2 men sharing the highest honour in physics for work done half a century earlier. And on the day it was announced, Higgs did a very Higgs thing. He was not reachable. He had no mobile phone, had never sent an email, did not own a television that he watched, and on the morning of the announcement he had deliberately gone out to avoid the media circus he knew was coming. He had a quiet lunch, soup and sea trout, in the Leith district of Edinburgh, and as he walked home a former neighbour pulled up in a car, an elderly widow, and congratulated him. He asked her, congratulations for what? She told him her daughter had phoned from London to say he had won the Nobel Prize. That is how the man found out he had won the highest award in science. A neighbour told him on the street because he had made himself unreachable. He was, by every account, deeply uncomfortable with fame for the rest of his life, a shy and private man dropped into a spotlight he never wanted. Known forever for a particle he wished had been named after more people, because here is the cruelty folded into the prize. The Nobel Prize in Physics can be awarded to at most 3 people. That is a hard rule, a self-imposed limit the Swedish Academy has held to for over a century, and there were, you will remember, 6 men across 3 groups who found this mechanism in 1964. Higgs, Englert, Brout, Guralnick, Hagen, Kibble. 6th the prize can hold 3. It held 2. 2, not 3, because of the deepest cut in the whole story. Robert Brout, Englert's partner, the the man who had worked shoulder to shoulder with him in Brussels and submitted their paper before Higgs submitted his, was not there to receive it. Brout had died in 2011. He missed the confirmation of his own life's work by a single year. He missed the Nobel by 2. And the Nobel Prize is never awarded posthumously, which meant that the one thing standing between Robert Brout and the highest honour his field could give was that his heart stopped beating in the wrong year. Inglet said, in the aftermath, that Brout would certainly have shared the prize had he still been alive. Everyone knew it. It changed nothing. The rule is the rule. A man did the work, waited most of his life, and died with the finish line in sight but not yet crossed. And the universe, or the machine, or the Swedish Academy, whichever you want to blame, ran the clock out on him. And the 3 men from Imperial College, Guralnick, Hagen and Kibble, who had found the same mechanism from their own direction in that same crowded year, were left out entirely, not because their work was wrong, because there were only 3 seats and the seats were spoken for. Tom Kibble responded to the omission with a grace that is almost harder to read than anger would have been. He said it was no surprise the Academy felt unable to include them, given the rule that no prize can be shared among more than 3 people. No surprise. He had helped crack one of the deepest problems in physics, and he was consoling the public about why he had been left off the honours, and he was doing it politely. There is a pattern in this field, and you can count it on your fingers. Brout dead before the prize. Guralnick, Hagen and Kibble waved off by a counting rule. Anderson, who arguably had the core of it first, speaking the wrong dialect to be heard. The credit for the origin of mass got handed out the way credit always gets handed out in science, which is to say unevenly, incompletely, and with real human beings left standing outside the door holding work that deserved better. But the injustice done to the people is not the darkest thing the machine brought back from that tunnel. The darkest thing was the number itself, 125 gigaelectron volts. And to understand why that specific number should unsettle you, why it kept some physicists awake in the years after the celebration, we have to go back to the valley, and the ledge, and the word I told you to hold on to. Remember the sombrero, the valley, the field that rolled off the central peak and came to rest at a value of 246. I told you that the field found a valley to rest in, and that the disturbing part was that it might not be the deepest valley. Now the machine has handed us the mass of the Higgs boson, 125 gigaelectron volts, and that number, combined with one other number, lets physicists do something they could not do before. It lets them calculate the actual shape of the valley. It lets them work out whether the ground we are standing on is really the bottom, or whether it is, as I have been warning you since the opening, a ledge with something deeper below it. The other number they needed is the mass of the top quark, the heaviest of all the known elementary particles, which weighs in at around 173 gigaelectron volts. The top quark matters because it interacts with the Higgs field more strongly than anything else, and so it has an outsized influence on how the shape of the field's potential behaves at extreme energies. Put the measured Higgs mass and the measured top quark mass into the equations of the standard model and run them, not at the energies we live at, but upward, to energies vastly higher than anything the Large Hadron Collider can reach, energies that existed in the first instance of the universe and that you will not find anywhere in the cosmos today. And the equations tell you something that, when the numbers first came in, made a number of very serious physicists go quiet. They tell you that our vacuum, the valley our Higgs field is resting in, is probably not the true bottom, that somewhere far below us are energies we describe with numbers like 10 to the 10th power gigaelectron volts and higher. The potential turns over and drops again into a deeper valley, a lower state, a configuration of the field that is more stable than the one we live in. The word physicists use for our situation is metastable. It means stable for now. It means resting in a dip, comfortable, seemingly solid, but not at the true lowest point. It means we are the pencil that fell and landed on a ledge partway down the mountain, and there is a longer drop still beneath us. This is not fringe speculation. This is what falls out of the standard model of particle physics, the most successful and precisely tested theory in the history of science. When you feed it the two numbers the experiments actually measured, the calculation was done carefully at the highest available level of precision in papers with titles that tell you exactly what they were investigating. A 2012 paper by Giuseppe Di Grassi and collaborators on the Higgs mass and vacuum stability in the Standard Model. A 2013 paper by Dario Butatso and collaborators with the almost unbelievably blunt title, investigating the near criticality of the Higgs boson. Near criticality. That is the phrase the physicists themselves chose. Not near stability. Not comfortably settled. Near criticality. Our universe, on the numbers, is sitting almost exactly on the boundary between a stable vacuum and an unstable one. Not clearly on the safe side, not clearly on the dangerous side, on the line. Let me tell you what it would mean, physically, for our vacuum to not be the true bottom, because the abstraction hides how total the implication is. If there is a deeper valley below us, then our vacuum can, in principle, decay into it. The way it would happen is through quantum tunneling. Somewhere, at some point in space, a tiny bubble of the true deeper vacuum could spontaneously form, the field inside it having dropped to the lower state. And if that bubble is large enough, it does not collapse back. It grows. It expands outward at very nearly the speed of light, and inside that bubble, the laws of physics are different. The value of the Higgs field is different. The masses of particles are different, and nothing that depends on the current laws, which is to say nothing, no atom, no molecule, no structure, no life, can exist. The bubble wall sweeps through space, converting our universe into the other one, the deeper one, and it does so at light speed, which means you would never see it coming. There would be no warning, no shimmer on the horizon, no time to react. The edge of the bubble travels as fast as the light that would carry any warning of it. By the time anything about you could possibly register that it had arrived, you would already be inside it, already rewritten, already gone. Now I have to be honest with you about the time scale, because the honesty is more unsettling than the doomsday version, not less. When you run these calculations and ask how long our metastable vacuum should be expected to last, the answer that comes back is a number so large it makes the current age of the universe look like an eye blink. If the standard model is the complete story, the expected lifetime of our vacuum is vastly, absurdly longer than the 13.8 billion years the universe has existed so far. We are almost certainly not going to be erased by a vacuum bubble tomorrow, or in 1 billion years, or in 1 trillion. On the numbers, the wait for spontaneous decay is longer than you have the intuition to hold. The honest scientist does not tell you the sky is falling. The honest scientist tells you something worse. The honest scientist tells you that the sky is balanced, for no reason anyone can find, exactly on the line between falling and not falling. Because that is the actual mystery here, and it is not the doomsday, it is the position. Fabiola Gianotti's number and the top quark's number place our universe not safely in stable territory. Not clearly in unstable territory, but right on the boundary between them. And there is no known law, no principle, no piece of theory that requires the universe to sit on that boundary. It could have been deep in the stable region. It could have been deep in the unstable region and never formed atoms at all. Instead, it is on the edge, balanced, and nobody can tell you why. Joseph Licken, a theoretical physicist at the Fermi National Accelerator Laboratory, put it about as bluntly as a physicist will in public. He said that it may be that the universe we live in is inherently unstable, and that at some point, billions of years from now, it is all going to get wiped out, and that this has to do with the Higgs field itself. He has described our position as being right on the edge between a stable universe and an unstable one, and then said the thing that should genuinely disturb you. There is no principle we know of that would put us right on the edge. We are not there because a law demands it. We are there for no reason we can name. Other physicists have used the same uneasy language. Some at CERN have talked about the standard model living dangerously, resting on a knife edge that no theory explains. The physicist Jose Espinosa, one of the people who did the careful stability calculations, said that we now know with a large degree of confidence that our vacuum is on the unstable side, while adding, correctly, that the lifetime is far longer than the age of the universe. Both halves of that sentence are true, and you are supposed to hold them at the same time. The vacuum is on the unstable side. The wait is longer than everything that has ever happened. And the question that neither half answers, the question that hangs over the whole business, is why we are anywhere near the boundary at all. This is where the abdication of authority is not a rhetorical flourish. It is the literal situation. The people who understand this best, the people who ran the calculations and know the numbers to more decimal places than I can pronounce, do not have an explanation for why the universe sits on this edge. They can compute that it does. They cannot tell you why. And a great many of them would strongly prefer, in public, to talk about almost anything else. Because near criticality is the kind of result that raises questions the field does not have answers to, and institutions do not enjoy standing in front of cameras describing the questions they cannot answer. But the edge is only the first of the two things the machine brought back that nobody wanted to say too loudly. There is a second problem, and in some ways it is worse. Because it is not about the far future, it is about right now, about the value of the Higgs mass itself, and about the fact that according to our best understanding of how physics is supposed to work, the number 125 gigaelectron volts should not be possible. Not rare. Not surprising. Impossible, in the specific sense that it requires a coincidence so precise that physicists have a whole crisis named after it. It is called the hierarchy problem, and it has been quietly eating the confidence of particle physics for decades. Here is the shape of it. In quantum field theory, the mass of a particle is not just a number you write down. It gets contributions from everything the particle interacts with, including the constant froth of virtual particles that quantum mechanics says are flickering in and out of existence in the vacuum everywhere all the time. For most particles, these contributions are manageable. For the Higgs boson, they are not. When you calculate how the froth of the vacuum should contribute to the mass of the Higgs, the corrections come out enormous. Not a little large, larger than the actual measured mass by many, many orders of magnitude. The natural mass of the Higgs, the mass you would expect from just adding up the quantum contributions, should be something closer to the highest energy scale in physics. The scale where gravity itself becomes strong, which is a number with 17 zeros more in it than 125 gigaelectron volts. The Higgs should weigh something astronomical. It weighs 125. That is a discrepancy of roughly 1 part in 10,000 trillion. And to get from the enormous natural value down to the small measured one, the various huge contributions have to cancel each other out, almost, but not quite perfectly, leaving behind a tiny residue that happens to be exactly the mass we observe. The cancellation has to be accurate to something like 1 part in 10,000 trillion. If it were off, in either direction, by an amount far smaller than a rounding error, the universe would look nothing like it does. The Higgs would be far heavier, the electroweak scale would be somewhere else entirely, and the delicate arrangement that lets atoms exist would be gone. Physicists hate this. They hate it viscerally, because it looks like a fix. It looks like someone reached into the machinery and tuned a dial to 17 decimal places to make the universe come out habitable. And physics is built on the deep assumption that there are no such coincidences. That when a number looks impossibly fine-tuned, it is because there is a mechanism you have not discovered yet that makes the fine-tuning automatic. That assumption has a name. It is called naturalness, and for 40 years it was one of the guiding lights of the field. The belief that the universe does not balance pencils on their points without a reason. For decades the field had an answer it believed in. The answer was called supersymmetry, and it was beautiful, and the Large Hadron Collider was supposed to find it. Supersymmetry proposed that every particle we know has a heavier partner particle, a superpartner, and that the contributions of these superpartners to the Higgs mass would automatically cancel the enormous corrections, naturally, elegantly, with no fine-tuning required. It would explain why the Higgs is light. It would solve the hierarchy problem. It would also, as a bonus, hand us a candidate for dark matter and hint at how the forces might unify. A generation of theoretical physicists staked their careers on it. Textbooks were written. It was, for a long time, not really a question of whether the Large Hadron Collider would find supersymmetry, but of how quickly and how many superpartners and what their masses would turn out to be. The Large Hadron Collider turned on. It found the Higgs, and then it looked for the superpartners in the energy range where they were supposed to be, the range where naturalness said they had to be if they were going to solve the problem they were invented to solve. It found nothing, no superpartners at the masses naturalness predicted, no new particles crowding in behind the Higgs to explain why it is light. The machine that was built to find the Higgs and its natural entourage found the Higgs, standing there alone, with none of the company that theory had promised. And every year the experiments push the possible masses of the superpartners higher, into ranges where they can no longer do the job they were invented for, where their existence would no longer make the Higgs mass natural, where invoking them starts to feel less like a solution and more like a hope kept alive past its usefulness. This is one of the quietest, most consequential failures in modern physics, and you almost never hear about it, because it is a failure of expectation rather than a dramatic discovery, and failures of expectation do not make headlines the way a new particle does. But talk to theoretical physicists honestly, and many of them will tell you that the absence of anything beyond the Higgs at the Large Hadron Collider is the most important result the machine produced. More important in a way than finding the Higgs itself. Finding the Higgs confirmed what everyone expected. Finding nothing else demolished what everyone expected. The Higgs came in at a perfectly natural-looking mass with no natural explanation, and the natural explanation everyone had prepared for 40 years did not show up. The field is left holding a particle it predicted, at a mass it cannot explain, sitting on a stability edge it cannot explain, with the theory that was supposed to explain both of those things nowhere to be found. Read that back, the greatest triumph in the history of particle physics, the confirmation of the standard model down to its last predicted particle, arrived hand in hand with the collapse of the field's confidence about what lies beneath the standard model. We got the answer to the question Higgs asked in 1964, and the answer came wrapped around two new questions that are, if anything, deeper and more disturbing than the one it resolved. Some physicists have responded to this by giving up on naturalness altogether, and where they go instead is somewhere that many of them find genuinely upsetting to say out loud. If there is no mechanism making the Higgs mass natural, if the fine-tuning is real and not the artifact of some undiscovered symmetry, then maybe the universe really did balance the pencil on its point, and the only reason we are here to notice is that in the vast majority of possible universes, ones where the tuning came out differently, there was nobody around to ask the question. This is the anthropic argument, and it is a kind of intellectual surrender that a lot of physicists resist with real emotion. Because it says the value of the Higgs mass has no deeper explanation at all. It is what it is, because if it were anything else, you would not exist to wonder about it. The universe is not fine-tuned for a reason. It is fine-tuned, and we are the ones who happen to live in the tuning that permits observers, out of an unimaginable ensemble of universes where the dials landed somewhere lethal. I want to be careful here, because this is exactly the kind of place where interpretations genuinely diverge, and I am not going to pretend otherwise. Some serious physicists still believe naturalness will be vindicated, that there is new physics just above the reach of the current machine, that a bigger collider would find it. Others think naturalness was always a prejudice, and the universe is under no obligation to satisfy it. Still others suspect the whole framing is wrong in some way we do not yet understand. What they do not disagree about is the data. The Higgs mass is 125 gigaelectron volts. The superpartners are not where they were supposed to be. The vacuum is near critical. Those are not interpretations. Those are measurements. And no interpretation currently on the table makes them feel comfortable. And there is a detail here that tells you how much the field feared this exact outcome, because the field had a name for it before it happened. In the years before the Large Hadron Collider switched on, when physicists imagined the possible outcomes. There was one outcome they dreaded above all others, and they gave it a name. They called it the nightmare scenario. The nightmare scenario was this. The machine turns on, it finds the Higgs boson exactly as predicted, and it finds nothing else. No superpartners, no new particles, no cracks, no doors, just the Higgs alone, confirming the standard model and pointing nowhere beyond it, leaving the hierarchy problem unsolved and the deeper questions unanswered and no experimental clue about where to look next. They called this the nightmare, because it would mean the machine had worked perfectly and told them nothing about what lies beneath. Would mean they had spent $10 billion to confirm what they already believed and close every promising path in the same stroke. That was the nightmare they named in advance and hoped to avoid. The nightmare scenario is what happened. That is not my dramatic framing. That is the term working physicists used before the fact for the precise result they got. The machine found the Higgs and it found nothing else, and the community that built it has spent the years since living inside the outcome it had specifically named as the worst one. When a discipline invents a phrase for the thing it is most afraid of, and then that exact thing arrives, you are watching something more than a technical setback. You are watching a field confront the possibility that the questions it most wants answered may be beyond the reach of the tools it knows how to build. And that is a quiet institutional grief that does not make it into the celebration reels. The photographs from 2012 show applause and champagne and an old man wiping his eyes. They do not show the slower realization, arriving over the following decade, that the machine had delivered the nightmare wearing the mask of a triumph. Therefore we should go back to the man, because the shape of Peter Higgs's life turns out to rhyme with the physics in a way that is almost too neat to be accidental, and because the way the field treated him is the same way the field treats the questions he opened. Higgs spent his life explaining why the universe has substance, why things have weight, why matter is solid and permanent instead of a rush of massless particles flying apart at light speed. He is the reason we can say, at the deepest level, why the world is heavy, and he himself lived one of the lightest lives imaginable. He owned almost nothing that a modern person would consider essential. No mobile phone, ever. No email. A television he did not really use. He walked to lunch. He read. He turned down a knighthood in 1999. He resigned from the campaign for nuclear disarmament when it broadened its opposition to include nuclear power, because he thought the physics deserved a fairer hearing than the movement was giving it. He left Greenpeace when he decided its stance on genetically modified organisms had become, in his view, hysterical and detached from the science. He was a man who would rather be right and alone than agreeable and wrong. The man who explained the weight of the world carried almost none himself. And there is the harder rhyme, the one that sits underneath the whole story. Higgs gave the universe its permanence and lived in permanent uncertainty about whether he had. For 48 years he did not know if the thing he had described was real. He held it at arm's length, by his own account, right up until the seminar ended and the wave knocked him over. He explained why matter is stable and spent most of his life unsure his explanation was true. And then, when the confirmation finally came, when the machine proved him right. The very number it delivered revealed that the stability he had explained is not permanent after all. The field that gives the universe its solidity is sitting on an edge. The man who explained why things last found out, at the end, that at the deepest level things might not. He got to be right. He did not get to be reassured. Nobody in this story got to be reassured. And notice what the institution did at every stage with the discomfort. In 1964, the theorists at CERN found the origin of mass uninteresting and let it drift because it did not look important, because it raised no fashionable questions. In 2012, the same institution, transformed, triumphant, spending billions, found the particle and celebrated. But the two problems the discovery exposed, the near-critical vacuum and the impossible lightness of the Higgs mass, those got far less airtime, because they are the kind of results that do not resolve into a headline and a photograph of applause. There is a consistent behaviour here across half a century, and it has nothing to do with conspiracy. It is simpler and more human than conspiracy. Institutions amplify the questions they can answer and quietly file the questions they cannot. In 1964, the answer looked absent, so the question got filed. In 2012, the answer arrived wrapped around new questions, so the answer got the stage and the questions got filed. The filing cabinet is always the same, only the contents change. You are told the story ends in triumph. A brilliant prediction, a heroic search, a Nobel Prize, an old man's tears. That is a true story. It is also the safe half of a longer story whose second half almost nobody tells you, because the second half does not end in triumph. It ends in two questions the smartest people alive cannot answer. About a field that fills the space you are sitting in right now, holding you together at a value it settled into for no reason, on an edge it sits on for no reason, doing quiet, invisible work that the universe has no obligation to keep doing forever. I want to bring this all the way in now, because everything so far has been out there, in the tunnel, in the equations, in the first instance of the universe, and the whole point of the Higgs field is that it is not out there, it is here, it is in the space between the cells of your body, it is in the gap between the atoms of your bones. Right now, as you take in these words, the electrons in your retina, in your brain, in the muscles of your hands, have the masses they have because they are in constant, unbroken conversation with the Higgs field, a field that is passing through you as surely as it passes through the vacuum between galaxies. You are not sitting near the field, you are soaked in it. There is not a cubic nanometer of you that is outside it. The reason your body holds its shape, the reason you are a stable arrangement of matter rather than a burst of light, is a value the universe settled on in its first trillionth of a second and has maintained, without your knowledge or consent, every instant since. Consider what that means at the scale of a single second of your life. In the time it takes you to read this sentence, Every one of the uncountable electrons in your body, and there are more electrons in your body than there are stars in every galaxy we can see, is interacting continuously with the Higgs field, drawing its mass from that interaction, moment to moment, with no gaps. Not once at birth, not once at the beginning of the universe. Now continuously, the field is not a thing that happened to you. It is a thing that is happening to you at this instant in every part of you at once, and it will keep happening for as long as you exist, and then it will keep happening in the atoms that used to be you after you were gone. You have never once in your life been outside it. You have never felt it, because you have never had a moment of contrast, never experienced the massless alternative, never known a single instant in which the field let go. The most intimate fact about your physical existence, more constant than your heartbeat, more continuous than your breathing, is a relationship with something you cannot see, cannot feel, and until a few decades ago did not know was there. It has been holding you the entire time, and nothing in any equation we possess explains why it should keep doing so. And here is the direct address I have been building toward, the thing I want you to actually feel and not just understand. If that value ever changed, if the field ever slipped from its ledge into a deeper valley, you would not feel it happen. You would not have time. The transition would arrive at the speed of light, which is the same speed as any signal that could warn you, which means the warning and the event arrive together, which means there is no warning at all. The boundary of a true vacuum bubble is not something you could see approaching, because seeing requires light, and the light announcing the bubble travels alongside the bubble, not ahead of it. One instant you are a person made of atoms held together by a field at 246. The next instant, with no perceptible gap, the field where you are is at a different value. Your atoms are not atoms, and there is no you to register that anything has changed. Not darkness. Not pain. Not an ending you could experience as an ending. Just a seamless substitution of one set of physical laws for another, in which you were never possible. Now sit with a question that follows from this, and that physicists genuinely discuss. If our vacuum can decay, and if the universe is unimaginably large, far larger than the part we can see, then has it already happened somewhere? Is there, beyond our cosmic horizon, beyond the distance from which light has had time to reach us in the entire history of the universe, a region where the field already slipped? Where a bubble of true vacuum is already expanding, already erasing, already converting the old universe into the new one at light speed. We cannot see it by definition, because it is beyond the horizon. And if it is expanding at light speed, it will never overtake the expansion of space between us and it. Or maybe it will, depending on numbers nobody can measure. The honest answer is that we do not know, and probably cannot know. But the question is not science fiction. It is a straightforward consequence of taking the near criticality seriously and combining it with the size of the universe. Somewhere out there, the ledge may already have given way. We would have no way to tell until the moment we stopped existing, which we would not experience as a moment at all. This is what the sentence Peter Higgs added to a rejected paper in 1964 eventually led to. Not just a particle, not just a Nobel Prize. A measured value that tells us the ground floor of physical reality is provisional, that the solidity of everything is a setting the universe chose and could in principle unchoose, and that if it ever does, the choosing will be silent and total and instantaneous and beyond any possibility of observation from the inside. The man wanted to explain why the weak force carriers were heavy. He ended up handing us a number that quietly asks whether the universe is permanent, and answers probably, but we cannot say why, and not necessarily, and you would never know. You might hope reasonably that in the years since 2012 the picture would have softened, that further measurements would have revealed some crack, some deviation, some hint of the new physics that would explain the impossible lightness of the Higgs and pull us back from the edge into comfortable natural territory. The opposite has happened, and the way it has happened is its own kind of quiet horror for the field. Since the discovery, the experiments have spent years studying not just whether the Higgs exists, but how it behaves. How strongly does it couple to each other particle? Does it interact with the top quark, the bottom quark, the tau, the W and Z bosons, in exactly the proportions the standard model predicts? Because the whole logic of the Higgs mechanism is that a particle's coupling to the field is proportional to its mass. The heavier the particle, the stronger the coupling, and this is a sharp, testable prediction that could easily have been wrong. If new physics were hiding nearby, it would most likely show up as a small discrepancy, the Higgs coupling to something a few percent more or less strongly than predicted, a thread you could pull. There is no thread. Measurement after measurement, year after year, the Higgs boson has behaved exactly as the standard model of 1964 vintage says it should. Its couplings line up with mass. Its decays come out in the predicted proportions. Every place physicists have looked for a deviation, hoping for a deviation, praying for a deviation, because a deviation would be a door out of the crisis. The particle has come back looking flawlessly, maddeningly standard. The Higgs is the most standard model particle imaginable. It is behaving so perfectly that it is closing every door through which salvation might have come. The dream was that finding the Higgs would be the beginning of a new era of discovery. Instead, the Higgs has turned out to be a wall, smooth and featureless. At the far end of the theory, with no visible handhold for climbing past it, there is one measurement still to come that the field is genuinely holding its breath for, and it goes right to the heart of everything we have been discussing. Remember the shape of the potential, the sombrero, the valley the field rests in. The exact curvature of that valley, how steeply the walls rise around the point where the Higgs field sits, is something that can in principle be measured directly, by studying how Higgs bosons interact with each other, how they couple to themselves. This is fantastically hard. It requires producing not one Higgs boson, but two at once, in the same collision, which happens far more rarely than the already rare single production. But if it can be measured precisely enough, it would tell us the actual shape of the potential in our own backyard, and from that shape we could pin down, far more tightly than we can now, exactly how close to the edge of stability we really are, whether the ledge is a gentle one or a sheer one, whether the deeper valley is near or far. That measurement is one of the central goals of the next generation of particle colliders, machines that have not been built yet, that would cost tens of billions, that some countries are debating right now. We are, as a species, seriously considering spending a fortune to measure, more precisely, the exact steepness of the drop we are standing at the top of. Not to prevent it, there is nothing to prevent, just to know. And there is a particular cruelty in what the Higgs represents for the theory as a whole, because it was the last piece. The standard model of particle physics predicted a specific list of fundamental particles, and one by one, over decades, every one of them was found, until only the Higgs boson remained, the final unchecked box, the last prediction standing. Finding it in 2012 completed the set. The standard model was, at last, experimentally complete. Every particle it predicted had been observed, and you might think completeness would feel like victory, like the end of a long climb. It felt, to a lot of physicists, like a door closing, because the standard model, for all its flawless precision, is known to be radically incomplete as a description of the universe. It does not include gravity at all. It does not explain dark matter, the invisible stuff that outweighs all the ordinary matter in the cosmos by roughly 5 to 1, that holds galaxies together and that the standard model has no particle for. It does not explain dark energy, the thing driving the universe to expand faster and faster. It does not explain why there is matter rather than nothing. And it cannot explain the mass of the very particle that completed it. The Higgs, in other words, did not just finish the standard model, it confirmed that our most successful theory has now told us everything it is ever going to tell us. And that everything is not nearly enough. We finished the map, and finishing it revealed that the map covers a small, well-lit island in the middle of an ocean we have no instruments to cross. The keystone went in, and the building it completed turned out to have no foundation under most of what matters. There is a deeper layer under even this, and it reaches back into the first moments of the universe, into the question of how the field came to be resting where it rests, and whether it was ever guaranteed to end up somewhere that could hold a person together. Because the settling of the Higgs field was not a gentle, inevitable thing. It was a phase transition, a moment when the universe, cooling from its initial fire, changed state. The way water changes to ice, the way a molten metal freezes. Physicists call it the electroweak phase transition, and it happened when the universe was a tiny fraction of a second old, when the temperature dropped low enough that the field could no longer sit balanced at zero on the peak of the sombrero and rolled down into the valley, and mass switched on across all of creation at once. That transition is one of the most important events in the history of everything, and we understand it far less well than the neatness of the story suggests. The details of how the field settled, whether it did so smoothly or violently, whether it happened everywhere at once or in patches that grew and collided, may be tied to some of the deepest unsolved questions in physics, including the question of why the universe is made of matter at all, rather than equal parts matter and antimatter that would have annihilated each other into pure light, leaving nothing, no galaxies, no stars, no you. Some physicists think the answer to that question, the reason anything survived the early universe, is hidden inside the specifics of how the Higgs field broke its symmetry, which would mean that the same event that gave particles their mass may also be the reason there are any particles left to have mass at all. The field did not just make matter heavy, it may be the reason matter exists to be made heavy in the first place, and the field's value need not have been what it is. Run the early universe again, with slightly different conditions, and the field could in principle have settled elsewhere, into a different valley at a different value, producing a universe with different particle masses, or no stable atoms, or no chemistry, or no possibility of anything that could be called a universe in the sense we mean. We are not living in the only outcome. We are living in an outcome, one settling out of a space of possible settlings, and the one we got is the one that sits on the edge of stability with a Higgs mass that requires impossible fine-tuning and no explanation for either fact. Every time you follow this back, it comes to the same place. The universe is arranged in a way that permits you, precisely, delicately, on a knife edge, for no reason anyone can find. And the man who first pointed at the mechanism behind that arrangement got a note saying it had no obvious relevance to physics. I keep returning to that phrase because I cannot get past it, and I do not think you should either. No obvious relevance to physics. It was said, second-hand, about the origin of mass by some of the best physicists in the world, in the year they could have understood it first. And you should feel something about that, beyond amusement at their mistake. You should feel a kind of vertigo about how knowledge actually moves through the world, how the most important thing in the room can sit on a desk looking unimportant, how the difference between a discovery that changes everything and a paper that gets filed and forgotten can come down to whether one annoyed man in Edinburgh decided to add a sentence to prove a point. The mechanism that gives the universe its weight was one editorial shrug away from drifting, unremarked, for who knows how long. It survived on spite. on the wounded pride of a shy man who felt his work had been misunderstood and decided to make it undeniable. And it survived that way more than once, which is the part that should move this from a charming anecdote into something closer to an indictment. Count the near misses. Philip Anderson had the core of the mechanism a couple of years before 1964, and it was passed over because he spoke the language of superconductors instead of the language of particle physics, and the particle physicists were not in the habit of reading the condensed matter people. That is one. Higgs wrote the model and had it rejected outright by the leading laboratory in the field as irrelevant. That is two. Brout and Englert in Brussels worked in enough isolation that Higgs did not know they existed until a referee told him. That is three separate groups nearly missing each other entirely. Guralnick, Hagen and Kibble came to the same result and decades later were counted out of the prize by an arithmetic rule. That is a field that produced, independently in triplicate, one of the most important ideas in the history of science, and managed at nearly every step to overlook it, dismiss it, isolate it, or leave someone standing outside the door. This is not a story about a few unlucky individuals. It is a story about how knowledge systems actually behave, and they behave like this consistently across every era, with every uncomfortable or unfashionable truth. The pattern is not conspiracy. Nobody sat in a room and decided to suppress the origin of mass. The pattern is something more insidious because it requires no villain. It is the accumulated weight of professional norms, of what counts as an interesting question this year, of which journals talk to which other journals, of the quiet gravitational pull toward the problems that are safe to work on, and the results that resolve into applause. That pull acted on Higgs's paper in 1964 and filed it as irrelevant, and that same pull is acting right now, today, on the two results we have been circling, the near-critical vacuum and the impossibly light Higgs mass, and it is filing them too, not because anyone decided to bury them, but because they are uncomfortable and unresolved and do not fit neatly into a triumphant narrative, and the machine of science, like every institution humans have ever built, prefers the questions it can answer to the questions it cannot. That is why you were handed the safe version, not because anyone lied to you, because the safe version is the one that resolves. Brilliant prediction. Heroic search, prize, tears, the end. It is a good story, and every part of it is true, and it stops exactly where the discomfort begins. The near criticality gets a paragraph in a specialist paper with a blunt title that almost nobody outside the field reads. The failure of naturalness gets discussed at conferences in tones of unease and then set aside because there is nothing to do about it. The absence of everything the Large Hadron Collider was supposed to find beyond the Higgs is the most important thing the machine ever did, and it is the thing you have heard the least about, because a discovery that things are missing does not photograph well. The filing cabinet from 1964 is still open. The contents have simply been updated. In 1964 we filed the answer because it looked unimportant. Now we file the questions because they look unanswerable. It is the same drawer. I want to stop here for a moment, near the end, and make sure the weight of what we actually know lands cleanly, separated from what we are guessing, because the discipline of that separation is the whole reason this is unsettling rather than merely dramatic. Here is what is not in dispute. The Higgs field is real. It fills all of space at a value that is not zero. It gives the elementary particles their mass, which amounts to roughly 1% of the mass of ordinary matter and 100% of the reason that matter can assemble into anything at all. The boson was found at 125 gigaelectron volts by two independent detectors at a confidence level that makes a fluke a 1 in 3.5 million proposition. It behaves exactly as the theory predicts. Those are not interpretations. Those are among the most precisely established facts in all of science, confirmed by the most expensive experiment human beings have ever performed. And here is the other thing that is not in dispute, the thing that all the disagreement sits on top of. Feed those established facts into the standard model and it tells you our vacuum is near critical, sitting on the boundary between stability and instability, and that the mass of the Higgs is fine-tuned to a degree that our deepest principle of physics says should not happen without a mechanism, and that the mechanism we expected is not there. Physicists disagree about what all of this means. They disagree about whether new physics will eventually explain it, whether the anthropic argument is a real answer or a surrender, whether a bigger collider would find the missing pieces or confirm their absence. They disagree about the interpretation. They do not disagree about the measurements, and the measurements are the uncomfortable part. This is the thing that prevents you from retreating to the comfortable thought that it is just one theory, just one interpretation, just one physicist being dramatic. It is not. It is what the numbers say, and every interpretation has to live with the numbers, and none of them makes the numbers feel safe. And underneath all of it, doing its work the entire time we have been talking, indifferent to whether anyone understands it or names it correctly or gives the prize to the right people, is the field. It does not rest. It does not switch off. It holds every electron in your body at its mass, this instant and the next and the next. A continuous act performed everywhere in the universe at once, in the vacuum between galaxies and in the space inside your skull, without pause. Without exception, without any guarantee written into any law that it must continue. We talk about the field giving mass as though it were a thing that happened once, long ago at the beginning. It is not. It is happening now. The conversation between every massive particle and the field it is soaked in is ongoing, active, present tense, the universe continuously deciding, moment to moment. That things will have weight. That decision has held for 13.8 billion years. Nothing requires it to hold for the next second, except the field's own inertia in a valley it fell into by accident, and rests in for no reason we can name. Return one last time to the question I opened with, the one I asked you to keep open, and see how much heavier it has become. Where does the weight of the universe actually come from? It comes from a field, filling what you thought was empty space, resting at a value it chose in a tumble at the beginning of time, on an edge no principle explains, at a strength no theory can derive, doing quiet, continuous work that lets you exist, and could, in principle, stop. That is the answer. It is not an answer that closes. It is an answer that opens onto a longer drop. There is a thread I left hanging near the beginning, and now is the time to pull it, because it closes the loop between the man and the dread in a way I find almost unbearable to think about clearly. Remember the boy in Bristol, reading the name Dirac off a school honours board, catching a particular kind of faith. The faith that if the equations say something is there, then it is there, and you go and find it. Dirac had predicted antimatter that way, by looking at his equation, seeing that it demanded the existence of a particle nobody had ever observed, and choosing to believe the mathematics over his own intuition about what was reasonable. He was right. The antiparticle was found. And Higgs inherited that exact faith, and used it to predict the boson, believing the math when it told him a particle must exist, and waiting 48 years to be proven right in a lecture hall in Geneva. Here is the part that should tighten in your chest. That same faith. The faith that vindicated Dirac and vindicated Higgs. The faith that says believe the equations even when they tell you something you did not want to hear is exactly the faith that now forces us to take the near criticality seriously. You do not get to keep the faith only for the comfortable predictions. The discipline that let Higgs predict a real particle from pure mathematics is the same discipline that now, applied to the measured mass of that very particle, predicts that our vacuum sits on an edge. If you believe the math enough to spend $10 billion finding the boson it predicted, you have to believe the math when the boson's mass turns around and tells you the ground is not solid. The honesty is not optional. The same faith that gives you the triumph gives you the dread. And there is no version of taking the science seriously in which you get to keep one and discard the other. Higgs believed his equation, and it made him famous. We believe the same equation, and it tells us we are balanced on a ledge for no reason. It is the identical act of faith. It just points somewhere darker now. And let me give you one number to hold in your body, because I have been throwing around the phrase fine-tuning, and it deserves to be made physical. The cancellation that keeps the Higgs mass small, the balancing of the enormous quantum contributions against each other to leave the tiny residue we measure, has to be accurate to roughly 1 part in 10,000 trillion. That is a 1 followed by 16 zeros. Picture it this way. Imagine balancing a full-grown adult on one end of a scale, and on the other end, grain by grain, pouring sand, until the two sides balance so perfectly that adding or removing a single grain of sand, 1 grain, would tip it. Now imagine that the adult weighs not what an adult weighs but as much as a mountain, and you still have to balance it, grain by grain, to the last single grain of sand. That is the precision the universe appears to have used in setting the mass of the Higgs, and our deepest instinct as physicists, the instinct called naturalness, screams that no universe balances a mountain against grains of sand by accident. There must be a mechanism. And we looked for the mechanism in the one place it had to be, with the biggest machine we have ever built, and the place was empty. You are living inside that balanced scale right now. Every atom in you depends on it holding, and nobody can tell you why it holds, or what is holding it, or whether the thing holding it is a law or a coincidence, or an accident that happened to permit observers in a universe that mostly does not. Touch something again. The same desk, the same phone, your own arm. Feel the weight of it, the resistance, the solidity that your whole life has told you is the most basic and trustworthy fact about the physical world. And understand now what you are actually feeling. You are feeling a field. You are feeling the ongoing, continuous, present tense work of the Higgs field, holding the electrons and quarks of that object at their masses. A field resting at a value it fell into by accident in the first trillionth of a second of the universe, on an edge that no law requires it to occupy, at a strength no theory can explain, tuned to a precision that our deepest principles say is impossible without a mechanism we have searched for and failed to find. The solidity is real. It is also provisional in a way you were never told. Every solid thing you have ever trusted is being held together, right now, by something that has no obligation to keep holding it, and that sits, on the numbers, closer to the edge of not holding it than to any comfortable middle. Peter Higgs died on the 8th of April 2024 in Edinburgh at 94 years old, in the city where he had done the work 60 years before. He died knowing he had been right. That is more than Robert Brout got, who died in 2011 with the finish line in sight and never crossed it. It is more than a great many scientists in this story got. Higgs got his confirmation, got his prize, got his moment in the auditorium when the wave knocked him over and the tears came. And I have been thinking about those tears differently the longer I have sat with all of this. We read them as tears of vindication, of an old man finally proven right, and they were that. But the number that proved him right is the same number that revealed the ground was a ledge. He wept at the confirmation of a field whose measured properties quietly announce that the permanence it provides is not permanent. He spent his life explaining why the universe is solid and heavy and stable, and lived to see the proof arrive wrapped around the news that solidity, at the deepest level, is a setting and not a law. He got to be right. He did not get to be reassured, and neither, now, do you. This is the thing you cannot unknow, and I am not going to soften it, because softening it would be a lie, and you came here for the version without the lie. The weight of the world is not a property of the world. It is a loan from a field you cannot see, resting at a value it chose for no reason, on an edge it occupies for no reason. Doing invisible work it is under no obligation to continue. The most important paper in the history of particle physics was rejected in 1964 for having no obvious relevance to physics, and the sentence its author added out of wounded pride predicted a particle whose eventual mass would tell us that the vacuum of space is not the floor, it is a ledge. And somewhere, possibly far beyond the horizon of everything we can ever see, possibly closer than we would ever want to know, the field may already have found the deeper valley. A bubble of true vacuum may already be expanding at the speed of light, rewriting the laws of physics as it goes, converting the universe of atoms and stars and people into a universe with different rules and no room for any of it. You would not see it coming. You could not. The light that would warn you travels alongside it, not ahead of it. One instant you are a person, held together by a field at 246. The next instant, with no gap you could ever experience, the field where you stand is at a different value, and there is no you left to notice that the ground finally gave way, that the ledge was always a ledge, that the solidity you spent your whole life trusting was, from the very first trillionth of a second, on loan and quietly, patiently, waiting to be called back.